Hi guys, it's Daniel here, and today we're going to talk a little bit about inversion. So what is inversion? It's a geometric transformation, kind of like a reflection, rotation, or translation, but it's a little bit more complicated. So to understand what it intuitively is, let's first talk about what a reflection is. If we have a line and that we want to reflect over, then basically what it does is it takes any point and you reflect it over like this to an equally distant point on the opposite side, and that is what the reflection is. So what this reflection transformation basically does is it maps points that are on one side of the line to map points that are on the other side of the line. So that's all nice and well, but what if we wanted to do the same thing with, say, a circle instead of a line? Well, clearly we can't have the same process going on by taking the point and going to the point on the circle nearest to it, then going equal distance away to our new point. This transformation won't work because, for example, say we had a point really far away from the circle. Then as we go to the nearest point on the circle and reflect over again, it'll end up on a point that is outside the circle again, which is not good. We want points to map from inside the circle to outside the circle. So instead, to alleviate this issue, we might want to have the points that are outside the circle be a little bit further away than the points that are inside the circle. For example, if we have a point here, if we want to reflect it over the circle, we probably want to have it end up being a little bit further away than before. And as we go closer and closer to the center, it would make sense for this to get further and further away until finally when we hit the center, it goes infinitely far away to some point that's infinitely far away, like if you just keep on going forever. And let's call that point the point of infinity. So what we have here is a mapping from this the points that are inside the circle to the points that are outside the circle plus a certain point at infinity. And this is just intuitively what an inversion is. So now that we have an intuitive understanding of inversion a little bit, let's try to find a more mathematical explanation. So this is what the actual mathematical definition is. If we have a point A in a circle with radius r, and we have a point O as the center, then A maps to A prime in the following way. It needs to satisfy that O, A, and A prime are all on a line. This follows our intuitive understanding, of course. But secondly, A and A prime are related by the formula AO times A prime O is equal to R squared. So this formula sort of gives what our intuitive understanding a more mathematical sense. And we can confirm that this follows our intuitive understanding because, say, first, if we pick A to be on the circle, then we get that AO is equal to R and A prime O therefore is also equal to R. So that means A prime is the same as A, so A maps to itself. And that makes sense. And otherwise, if we have, say, A gets really, really close to O, then AO gets really, really small, and A prime O therefore has to be really, really large for them to multiply to this constant R squared, and that just corresponds to having A prime be really, really far away, which is also good according to our intuitive explanation. So it seems like this formula is a good one. Okay, so now we know this formula is a nice one that we can work with. Then the question now becomes, well, what do the lengths become after inversion? Like what is the new distance between 2 points after you invert about a circle with radius r? Well, to answer that question, first let's look at a diagram that we've already discussed just that second ago, which is what is the new length A prime O compared to AO. What is the formula for this? And, well, the formula that we just came up with just gives this automatically if we rearrange it, as A prime O is equal to R squared over AO. So that's the correct formula for the distance between 2 points after an inversion where one of the points is O. But now comes the question, what if both points are not O? For example, if we had another point B, which inverted to, say, B prime. So what is the distance A prime B prime compared to AB, and maybe some other lengths? So in order to solve this problem, we first need to make a nice observation, which is that OA times OA prime is equal to OB times OB prime because they're both equal to r squared. So that means by power of a point, we know that in fact these 4 points, A prime, B prime, are actually concyclic. They're on the same circle by power of a point. And so we can angle chase here a little bit to find that angle OAB is equal to 180 minus angle A prime AB, which is equal to angle A prime B, and similarly angle OBA is equal to angle B prime A prime. Or no, that's not right. OBA is equal to angle A prime B. And finally, we know that, of course, angle AOB is equal to angle A prime OB prime since they're the same angle. So, in fact, we know that triangle OAB is similar to triangle OB prime A prime. So now we have these similar triangles. We can probably use the relationship between them to find A prime B prime in terms of AB and some other lengths. So let's go ahead and do that. We know that from the similarity, A prime B prime over AB is equal to, say, A prime O over BO. So that means A prime B prime is equal to A prime O times AB over BO. But here's the problem. We still have an A prime in this formula, and we don't really want to have the length of A prime B prime still depend on one of the new points. We just want it to depend on the old points, A, B, and O. But we can do that because, look, we already have this formula, A prime O is equal to r squared over AO. So we can go ahead and use that to get this is also equal to AB times r squared over AO times BO, and that is our general formula. A prime B prime is equal to AB times r squared over AO times BO. Now that we know a little bit about inversion, let's try to use it on a problem. And for this problem, I'm actually going to prove Ptolemy's inequality. Ptolemy's inequality. And this states that given 4 points A, B, C, D in the plane, we have that. If we consider all these lengths right here, we have that AB times CD plus AD times BC is greater than or equal to BD times AC. We're going to prove this inequality. So at the moment, this doesn't look very easy, but let's try to use inversion and see how much simpler it gets. So for this problem, let's invert about point A. So let's use a circle with center A and radius. Let's just say this radius is 1. Alright, so the radius is 1 and the center of the circle is at point A. So now let's invert each of these points to their new points, B prime, C prime, and D prime, and then see what we need to prove using the points B prime, C prime, and D prime. So using our formula, we know that AB goes to r squared, but r is 1, so 1 squared, which is just 1, over AB prime. CD goes to C prime D prime times r squared, which is just 1 again, divided by C prime A times D prime A. Now what about the next one? AD goes to 1 over AD prime. BC goes to B prime C prime over, B prime A times C prime A. And finally, we want this to be greater than or equal to, BD is equal to B prime D prime over B prime A times D prime A, and AC is just 1 over C prime A. So now we take a look and wow, all our denominators are AB prime times AC prime times AD prime. So let's multiply both sides by that and clear all of that away to leave us with C prime D prime plus B prime C prime is greater than or equal to B prime D prime. And if we take a look at this, well, this is quite familiar to us because this is actually just the triangle inequality. Given a triangle, given 3 points, the triangle inequality is always true. So CDB, C prime, D prime, B prime. This is always true by the triangle inequality. So actually, we just proved Ptolemy in basically one line. So that's pretty cool. Quite a useful transformation, if you ask me, and quite an unexpected application of inversion, actually. But yeah, this is just a bit of a introduction to inversion, mainly focusing on lengths. If you guys want to know more about inversion, leave a comment, and I might go into more detail about some other points of inversion, because inversion is a very versatile transformation. It's a very interesting topic to talk about, and considering the lengths is just the tip of the iceberg. So leave a comment if you're interested, and thanks for watching. Hi guys, Daniel here, and I know the ARML is coming up in probably less than a month. I forgot. But anyways, because of that, let's do an ARML problem.